What's up, guys? So today let's talk about matrices. Okay, so the idea is that people only discuss the linear transformation, but somehow linear transformation is a little bit maybe abstract, right? Because you only talk about a vector space, the function map from vector space to vector space such as satisfied the common property. And then we collect and then we discuss the home VV as a AOV, and we say that this is not just a vector space, but it's a ring. It's also algebra. And then we can study the minimum polynomial and the eigenvalue and eigenvectors. Okay, so today we need to establish the relation about the linear transformations and the matrix, and we will prove that they are actually the same. So after today, or after this video, I will abuse my notation. So after this video, when I say linear transformation and matrix, I will look them as equal. Okay. So yeah, so I think the idea is very easy, right? Because if I from V to, let's say, V to V, right, and I can create a basis, let's say V1 to Vn and V1 to Vn, and dimensional V is finite dimensional. Okay, so I can write TV1 as the linear combination. So I like alpha 1 V1, like alpha 1 2 V2, alpha 1 and Vn, right? And the TV2 is basically written as alpha 2 1 V1. Okay, so to be simple, just T of Vi will be summation of alpha ij, Vj, from 1 to n, right? Yes, okay. Okay, so this is the definition, right? So then I can define a matrix representation of T, or sometimes I written as a bracket T as the alpha 1 1, alpha 1 2, alpha 1 n. Okay, so this is just the definition. Okay. Okay, so immediate theory. So if lambda 1, lambda 2, lambda n are eigenvalues of T, and they are all distinct, So that means I can find V1 such that TV1 is lambda 1 V1, and the TV2 is lambda 2 V2, and the TVN is lambda n Vn, right? So in this basis, our T will be looked as the diagonal. Okay, so this is called the diagonal line. So if there is a vector basis such that the matrix look this, then we're saying that this matrix is diagonalizable. Okay. So we proved that. So the previous theorem tell me that if we have undistinct eigenvalues, then this matrix T will be diagonalizable. Okay. Okay, so somehow, so now we definitely have the matrix, right? So let me differ. So I should say what's two matrix addition, right? Okay, so suppose this T is let's see. So suppose this T is written as tau ij, right? For each ij color, ij indexes, and as written as let's say sigma ij. So I just define T plus S for each ij component will be, let's say this is X. So Xij defined to be tau ij plus sigma ij. Okay, so you exercise that this check. So you can check that this is consistent with you abstractly add these two linear transformation and make it as a matrix, right? The reason is that your TVI will be let's say tau ij Vj, right? So, and then your SVI will be sigma ij Vjj, right? So you sum of this, you get T plus SVI will be J tau ij plus sigma ij Vj. So this tells you that the addition of the linear transformation match exactly with the definition of the matrix, addition of definition of matrix. Okay. And then next is the composition. Okay, so the composition of matrix, I think everybody knows, right? So yeah, so the composition of matrix, if you times TS, let's say this is let's say tau ij, and this is sigma ij. Then you times this, the ij component will be summation of tau ik sigma kj. Okay, k from 1 to n. Okay, so this is the definition, right? So for the matrix representation, so the key is that we need to we hope to show this is consistent with the TS. Well, this is consistent of our matrix representation, our abstract linear algebra sense. So what I'm saying is that I hope to prove that this TS, I hope to prove that if you times this TS ij, abstractly I define to this, and we hope to actually compute this in a abstract algebra, in a linear transformation sense, and we take a matrix representation, and then make sure that it coincident with our usual definition. Okay, so should be trivial, right? So let's take T as Vi. So from here we get a T. I use K, right? So I use this is tau ik vk k, and I use J, right? So it's Tk tau ik tvk. So it's kj sigma ik Tkj, right? So Vj. Okay, but my convention is that any linear transformation act on Vi, I written as alpha ij Vj, right? So this is the ij indices. So I need to respect to this, right? So from here that our ij results, the TS matrix rep should be sigma ik tkj. So this is you see, so this proves that our definition actually works as the same. Okay, so this also proves, this also shows for any three matrices ABC, you will have A B C equals A B C. Okay, so since you view as a function composition. Okay, so from now that we know that T plus, we prove that we show that the matrix. So we show that if we get T plus S and using and write as a matrix, we get T plus S. And then we also prove that this TS matrix representation as our usual TS sense by this special multiplication. It's called matrix multiplication, right? Okay, so what I'm saying is that final results will be the linear transformation, 1-to-1 onto to the all the matrix. So once you fix the basis. So idea is that once you fix the basis, then any linear transformation abstractly will have the concrete representation matrix, and then you fix the matrix, and then you fix the basis, and you go back, you get a 1-to-1 correspondence. Okay, so it means that this AV is the same in the n dimensions, the same as the so-called matrix algebra with the field F. Okay, so this is what we have achieved. Okay. So this is called algebra homomorphic. Okay, so final theorem. This theorem tells me that if V is finite dimensional, and then for our matrix T has a basis V1 and Vn, and another basis called okay, so let me just change the notation. So N1T is one basis, one representation of the matrix with the basis V1, Vn, and N2T is another. Okay, so V1 prime, Vn prime. Okay, so theorem tell me that there exists a C such that it's n by matrices such that they are similar. So N2T equals to C N1T, C inverse. Okay, so by the way, this inverse is well defined. Okay, so yeah, this is our so we need to prove. Okay. Okay. Yeah. So yeah, so the key is to find C, right? So key to find C. Okay, so this should not be difficult, right? So the idea is that let's define SV. So let's define SVI to be let's define a linear transformation such that SVI will be what will be VI hopefully VI prime, right? So I define a linear transformation as such that SV1 will be V1 prime, SV2 will be V2 prime, the SVN prime, SVN will be VN prime. Okay, and then we take C is a matrix representation of S. Okay, so let's do the proof. Yeah, so proof is simple, right? Because TVI is supposed TVI is alpha I J V J J J, and the TVI prime will be let's say beta I J VJ prime. Oh, also. So VJ prime should be viewed as called V. I mean, you can pronounce it V prime J, right? Because V prime, because J should be always there's only one, but you call it J prime also okay. So what I'm saying is that you just need to remember that they are different sets. Okay. Okay. So forget about what I'm saying. Okay. Okay. So from here that we by the way, so once I get this, I know that S is invertible, right? Because map to base is the base. Okay, so so from here that we have we just need a change a variable, right? Let's see what okay, so I can just directly take these to be these, right? So I get TVI prime equals to J beta IJ, let's say SVJ, right? Okay. Okay, and I also plug in this, so I get T SVI equals to J beta IJ SVJ. So you have this. Okay. Okay, so from here, I get that so from these two, right? We get TS VI equals to this, right? So which tell you that the matrix representation of TS will be this, just this guy, right? So it's basically let me see. I think yeah, should be this, right? So the matrix representation of TS is basically, or basically I can take the inverse of going to this. So let me just write down. So I should take a TST inverse VI. We'll get the J beta J VJ, right? So I take as inverse. Okay. So the matrix representation of STS inverse will be just this T prime. Okay, and then you can do the multiplication and you get the answer. Okay. Okay, I think that's it. Okay, so see you guys next videos.